SN2 reaction. So every mechanism in organic chemistry has an abbreviation like that. So SN2 stands for substitution nucleophilic bimolecular. So substitution is exactly that, as you saw with the radical mechanism. CH going to CX, where X is chlorine or bromine. And now that we have an halogen in the molecule, we're going to substitute it for some other functional group, and then learn the parameters of how that's possible. So the nucleophilic, we'll learn those terms, nucleophile, electrophile, as they relate to Lewis acidity. And then the 2 is bimolecular, and so that deals with the rate. So for module 4, we'll learn SN2 and SN1. In module 5, we'll learn another mechanism called E2 and E1, and that stands for elimination. So if you are carrying on in the spring, these mechanisms will be revisited in that semester as well. And again, the word substitution comes up a lot, so it's changing one group for the next. So we'll look at the arrow curve, arrow pushing formalism for that, how the electrons move, what bonds are made, and what bonds are broken. Any questions before we get started? So to put this into context, we'll revisit the molecule that we started this semester on, AZT. And I think by the end of Wednesday or early Friday, you'll see how AZT is made from a starting material over multiple steps and what the issues are. So I have a collaborative project in my research group with Jacques Kessel, who's a biochemist here. And my group makes small molecule HIV integrase inhibitors for his group to test. And so Kessel is an expert on studying the HIV integrase enzyme. And so this is a slide we share and we show about the rate of infection in Mississippi. You can go on the website, I think it's hiv.org, and you see the entire country. But what you see here are these different colors, and then down here is the key with the rate. So within the counties, you can see the rate of infection. And so one of the things that you will see on your student course evaluation, and I've been reminded to tell you to please fill those out by the provost office, is have concepts been brought up in class that make this relevant to the real world? So again, HIV is one disease that exists in the world. There are many diseases, right? And so HIV is no longer considered a death sentence because these molecules exist that help people live manageable and healthy lives. And so there is one molecule, AZT, is shown on the slide. And I sort of stripped out most of the other slides I had on this, but the HIV life cycle has like 7 to 8 key steps that happen. And the molecule that you see interacts with a certain stage of that life cycle. And its therapeutic indication is a reverse transcriptase inhibitor. And so patients that are HIV or infected with AIDS usually have a maintenance that they have to take every day of a pill that will interact with each stage of that life cycle. And so AZT is typically one of them. And if you look, one pill of AZT has 300 milligrams of that as the active pharmaceutical ingredient. So a patient must take that twice a day. So that's 600 milligrams per day. You multiply that out by 365, then you get the amount that one patient has to take per year. And so in 2019, it was estimated 37,800 new HIV infections occurred in the US. So that's just the new ones. That's not counting for the existing ones. And so the question is, how much AZT is required to be produced per year? So are there any pharmacy techs in the crowd? Anyone work at CVS or Walgreens or anything? I'm sure that even if you've gone to Moffitt and you've got a prescription for something, you see all the bottles on the shelf, right? So take a guess how many bottles are there. It's quite a bit, right? So AZT is like one bottle of hundreds sitting on that shelf. So as you'll see through the math, just for this one drug, it requires a lot of material. And the connection to the real life between organic chemistry and this is that molecules like this, you can't harvest them from the ground. Nothing produces them. You can't, extract it out of something. It has to be made. So it's made through organic reactions, and the goal of any reaction is to produce one thing in 100% yield. So you're not generating waste and you're not generating byproducts that you have to purify. And the reason for that is, if these patients need medicine, they can't wait 3 months because the next batch has to be made. So the pharmaceutical industry is very important in everyone here living a nice, healthy life. Without violating HIPAA, I'm going to assume that everyone here has at some point taken a prescription drug. And those drugs, again, they don't come from the ground, an animal or a plant or anything. They have to be made. So if you think about that pill all the way back to the research, it's quite involved. So as highlighted in green here, a patient requires about 220 grams per year. And for just the new patients, you multiply that by the 37,800, you get 8,278,200 grams, which is 8.272 metric tons. So have you run any reactions in lab yet, your 255 lab? You run a reaction to isolate a product. So what was your yield of that reaction? 13%, something like that. You knocked half the beaker over, it spilled. So imagine, when companies run these reactions, they're run in very large vessels. I mean, they're running these on tens, if not hundreds of kilogram scale at a time. And so there's a lot of factors that go into that. And, making a metric ton of anything is quite intimidating. So this, again, it's just one drug of what you see on the pill bottles in the pharmacy. So approximately 1.2 million people in the US have HIV. And if you then do that math, that's 262 million grams of AZT required per year. That's just in the US. In other countries, the disease has a higher prevalence, primarily due to education, I would say. People are not educated about sexual activity, and that's how the disease gets transmitted. So as you see on the left here, AZT starts from thymidine, and then over a series of reactions, it's converted into the drug. And just looking at it, what looks different to you? So the OH group here, I want the highlighter. The OH group here, it's been substituted for an azide. So that's substitution. What I will further point out, and what we'll, again, probably learn on Wednesday or Friday, is everything that you've learned so far, you can identify different functional groups in that molecule. The reason this says reactions plural is that you have to deal with some of these other functional groups before you can actually get to what you want to do. If you'll notice, there's 2 alcohols in here. You have the primary alcohol and the secondary alcohol. And you specifically want to substitute at the secondary alcohol and not the primary, so that is an issue. And then there's other things to deal with that we've learned about. Acidity of functional groups, that's going to matter. And then pertaining to the SN2 reaction, not only has the OH been substituted for N3, it's in the same disposition. And so it's, the word we use is retention, because that carbon is a stereogenic carbon. The azide stereochemistry has been retained in what you see in the secondary alcohol. And so, as I said, we're farther and farther away from the shore of what you sort of know already, and we're learning these new things. And part of that is all of these complicating factors that come into play for a mechanism. So again, OH going to N3 is substitution. Again, that's just one functional group for the next. So the way that I teach, this part of the semester moving on and then going into Organic 2, I like to talk about the oxidation state of carbon. So I abbreviate that OS. And I use, I think, a simpler tool than what many textbooks present this as. And what you're going to do is just look at any carbon and count the number of bonds to the heteroatoms. And then we call that an oxidation state. Because you've learned a lot of functional groups so far, one way to manage all the information is how do the reagents act upon oxidation states? And then if you can control the number of oxidation states through a sequence, the better your outcome of producing that product in high yield. So we're simply going to count bonds to a heteroatom. So heteroatoms are not C or H, but any of these listed here. It says, for example, the carbon-bearing, the secondary alcohol, we would say that's an oxidation state of 1. And then in the product, that carbon is still at an oxidation state of 1 because it's a carbon-nitrogen sigma bond. So we'll walk through this exercise and then we'll get into how substitution actually occurs. So of the three oxidation states, 1, 2, and 3, you have a couple functional groups listed, and it's asking you to classify them according to the correct oxidation state. So I'll let you think about it. I'll grab a sip of Mountain Dew, and then we'll check in. So what do you think is the best response? So C. So an alcohol is always going to have a sigma bond from carbon to oxygen. So there is an example. A ketone always has a pi bond. So you have a sigma and a pi bond, so a double bond, that's 2. And an ester has 3. And again, the reason for using this classification system is as you learn more reagents, those reagents will really only act upon certain oxidation states. So it helps you determine in a molecule that has many different oxidation states where the reaction is going to happen. So that concept that I mentioned is called chemoselectivity. In the last lecture, we saw regioselectivity, where you have a pi bond and the elements can add to different carbons. In this one, we're talking about, if you have oxidation state 1, 2, and 3 functional groups, which one does the reagent prefer to act on? And probably the reason that I went into organic chemistry as a profession is once you know all these reactions, that's like your sort of moves in chess, if you're familiar with the moves. And then to win the game of chess, you have to sequence those moves properly so that you get the check and the checkmate. So you not only have to know the reactions, but then to get the desired outcome, you have to sequence them in the right order. Otherwise, you're going to get a byproduct or, some isomer that you don't want. So take a look at this using the definition of oxidation state. And how many oxidation state 1 functional groups do you see? Huh? We have 3. There's one that might be a smidge ambiguous, and I'll point that out, but there's 4 total. So this carbon primary alcohol. That carbon is part of an ether. Secondary alcohol. Probably the weird one is this one right here. So it's a carbon-nitrogen sigma bond, and it's part of an enamine functional group. So total, we would say there's 4. Now, to put it into context, if you had some reagent and it acted on oxidation state 1 functional groups, then your next question is, okay, which one? And then if you're, not comfortable with the fundamentals, that's like your boat and you lose your oars. You're at the mercy of the current of the sea at that point. So oxidation state 2, how many of those are there? Or to 2. Again, probably the best way to do this is, pick a starting point. So if that carbon was a starting point, you really just walk along the backbone and you answer the question for each carbon. So the molecule ends up only having 1. And so it's right there. So that carbon has a sigma bond to an N and an O. And that's called an aminal. So as I said, that carbon So probably why that one's tricky is because you're used to seeing like a double bond, like a carbonyl. That would be oxidation state 2. But a carbonyl carbon is sp2 hybridized. This one's sp3 hybridized. And then what about oxidation state 3? How many of those are there? So just 1, that would be the amide. And then oxidation state 4, which for carbon is the highest oxidation state. There's just 1, and that's called a urea. So notice this common nitrogen is involved in functional groups with 2 different oxidation states. So the latter, if I can summarize yet question. So you're counting the bonds, not the atoms. So sigma, sigma, pi, sigma. So the sort of ladder, if we start with, did something move? Okay. If we start with methane, that would be an oxidation state of 0. And then if we made methanol, that would be 1. If we made formaldehyde, that would be 2. Formic acid, that would be 3. And then carbon dioxide would be 4. So oxidation state 4 is the highest for carbon. So if the number increases, that's called an oxidation. If the number decreases, it's a reduction. So again, those are ways to help you manage all the different reagents that we're going to learn. You know, looking at the starting material to the product, was the carbon oxidized or reduced? If it stays the same, then it's not an oxidation or reduction. But again, that's going to help us with the strategy part of sequencing the reactions. So again, the urea was at an sp2 hybridization for oxidation state 4. But as I showed in the last slide, you know, carbon dioxide is sp hybridized. So those are always things that you want to keep in mind as we're looking at learning these new mechanisms as well. So I asked this last semester and it was, I guess, kind of confusing, but I'll just write everything out so you understand the intent of the question. So it's asking you, what is the sum total of all of those? So for each one, we're going to list how many there were and then add that number together. So for oxidation state 1, we said there was 4, 1, 1, and 1. And so the sort of intent was that you multiply that. So the way that I think about it, it has an oxidation state total of 13. And again, as we learn these reactions, we have to manage that, because as the oxidation state increases and you want to do further reactions, you're going to have a harder time specifically isolating where the reaction occurs. Any questions before we get into it now? Yeah.
Where would you get the
I think it's you can get enzymes that produce it in large quantity. So like, I'm not a biochemist, so I could be talking absolute shit here, but like you can engineer like E. coli and stuff to get it in these large vats, and then I'm not terribly familiar with enzymatic reactions, but you know, you have this enzyme in there and you feed it, you know, the sucrose and all that other stuff. You get this medium and then it's going to produce it, and then you can separate it out. So here is a a substitution with one carbon. Now, what is sort of not shown is all the intricate details of what substitution involves, and I hope to just introduce those a little bit at a time rather than showing you the whole sort of shebang at once. Because as I said, there's a lot of nuance to this that must be considered. So let me highlight some things here. We're going to start with bromomethane. And sodium hydroxide. We've seen sodium hydroxide in the context of it acting as a base, where the job of the base is to abstract a proton. But if you look at the reaction, a proton has not been transferred. A substitution of bromine for OH has occurred. So this necessitates a different mechanism for that reagent. So instead of using the words acids and bases, we're going to use two other words, nucleophile, electrophile. In this case, the sodium hydroxide is the nucleophile, and the bromomethane is the electrophile. And those, again, will relate back to the Lewis acid-base definition. Simply put, the nucleophile supplies the electrons, the electrophile accepts them. So to understand why this happens, which of the following best describes the carbon halide CX bond of a haloalkane? Keeping in mind that the halogen has 3 lone pairs of electrons. So it's a covalent bond. That's one. So that's what the line means. It's a polar covalent bond because with X being halogen, we know that the electronegativity of that element is greater than carbon. And then we can assign the delta minus to the halogen because of those lone pairs, and that makes carbon delta plus. The delta plus is what is indicating to you that that carbon wants to accept electrons from the nucleophile. So we would say B. And again, this mechanism of substitution only works on polarized covalent bonds. The nonpolar CH bond, again, that was the radical substitution. So from CH to CX, you do radical substitution. Once you have the X group in there, now we do the SN2 mechanism. So as shown in the reaction below here, the arrows work the following way. The nucleophile has to attack the electrophile. So sodium hydroxide has the 3 lone pairs on oxygen. Those will attack the delta plus carbon of that polarized bond. So we're making an OC bond, and then we're breaking a CBr bond. So that carbon is accepting, and then the bromine is accepting the electrons in that bond. So this part right here is called the leaving group, or LG. Another thing we have to talk about is the timing of how those arrows move. The nucleophile attacks the carbon, and then that carbon leaving group bond is breaking. In the timing of that, we want to think of it as sort of concerted in a way. We're going to learn another mechanism called SN1, where the timing is very different. And so the final sentence here says, the nucleophile attacks the electrophile at a 180-degree trajectory to the CX bond. And so why is that? So we're drawing these things, again, on the slide as lines. But keep in mind, those lines mean orbitals. So as highlighted here, you have a carbon-bromine sigma bond. But for carbon and bromine to bond, you have 2 elements, the carbon and the bromine. They're each supplying an orbital. That makes 1 orbital. Due to the conservation of things, you have to have another orbital. That's called the sigma star, or anti-bonding orbital. So as highlighted down here, the sigma star orbital sits 180 degrees to the sigma orbital. So the anti-bonding is designated by that star or asterisk. And just sitting there, it's empty. In terms of an energy, you have your 2 electrons in the sigma bond, and so the sigma star is empty. So when the nucleophile attacks, it has to go into some orbital to form a new bond. So that lone pair of electrons is going into the anti-bonding orbital. And then subsequently, within a short period of time, the sigma bond is then breaking. So we'll see more of this stuff in 256. When we talk about color, so I don't want to tilt this too much, but you can see my Mountain Dew is yellow. Like, why is it yellow? So there's yellow dye number 5 in there, right? If you read your can of anything, they always add dyes and stuff. And so why is one dye red and one's blue or yellow or what? So that has to deal with bonding and anti-bonding orbitals within an organic molecule. The other thing I want to point out now with the highlighter here, I know it's subtle, but it's important. So I'll use blue. I'm going to use blue for that hydrogen. Green for that one. And then yellow for that one. So not only is the bromine substituted for OH, look at sort of the side those hydrogens occur on. So here I would say they're on like the left side. And then in the product, they're on the right side. So due to the nature of how this attacks, the carbon has undergone inversion. And again, when it's just 3 hydrogens, it's not a big deal. But if you imagine those colors, the blue, green, and the yellow, if they were all different, there would be 3 different substituents. You're adding a 4th one, and then that impacts the stereochemistry of that carbon. So there's again, no getting away from everything we've learned so far this semester. It's all sort of coalescing at this point where we're putting it into use. So keeping in mind everything you know, everything we talked about, which of the following will not undergo an SN2? So I heard some A's at the start here. Why is that?
No hydrogens.
Say what?
No hydrogens.
There's probably a better explanation. Yeah.
I think it's sp2, so it's trigonal planar, right? So the sigma star bond is not very accessible or something? Is that?
So that's the one that's different, right? B, C, and D. The carbon bearing the leaving group, those are all sp3. So A is different because it's sp2. And again, if this was the sigma bond, the sigma star bond has to be right behind it. And what is sitting right behind that is this other carbon. So a nucleophile cannot get past that carbon into that bond. So now we're sort of in the realm where we're thinking about these mechanisms. The space in which things happens will matter quite a bit. And especially in Module 5, the Newman projection is going to come back to haunt you because that's going to matter as well. Yeah?
What is
SN2 stands for substitution nucleophilic bimolecular. So sp2 and sp under this mechanism do not work. So if you see a substrate with a leaving group at that hybridization, you can say, okay, nothing is going to happen there. And the reason for that is due to the orbital alignment not being accessible. So what is SN2? Again, the 2 stands for bimolecular. That means the nucleophile in the electrophile must be in the reaction for this to proceed. And ultimately, that's relating to the rate. So think of rate as like traffic. What is the rate at which you get your chicken nuggets from Chick-fil-A? Probably pretty slow, right? So again, kinetics is about rate, and the rate equation is shown here. The nucleophile, electrophile, that's your 2. So the concentration of those things will matter in terms of the overall rate. And then you have this thing K, that's your rate constant. So the square brackets mean molarity. So for any mechanism, there's always an RDS, or rate determining step. And that's best visualized with the reaction coordinate. So if we're thinking about 3Ds and hiking on a hill, the highest hill of your trail is going to be the rate determining step to how you get to the finish line. That's where you expend the most energy. That hill is called the energy of activation. And the top of that hill is called the transition state, or TS, which is designated by the dagger symbol. Is anyone a Microsoft Word expert? It's like Option Shift 3 or whatever is the dagger symbol. Don't worry, you'll learn them eventually. So here's the coordinate with time as the x-axis, as we've seen. On the left are your starting materials. So again, they're at some energy. So we want to determine a couple things. The location of the rate determining step, which is the energy of activation, and then the location of the products relative to the starting material. Is it above or below that line? And now the difference between what we saw for the radical substitution is this. This is now called delta G, and that's the free energy. Anyone know what the G stands for? What? What? So Gibbs, so he was a physical organic chemist, I believe won a Nobel Prize for this work. The Gibbs free energy describes everything in that system. So before we were only determining enthalpy, H. So now there's other things in this equation which we have to consider. So we see the nucleophile attacking the sigma star. We're then breaking the sigma bond. We're going uphill in energy. So the highest point there is that transition state. And this is where I said things start looking weird, because if you look at that carbon, you can think of it as sp2 hybridized, where in the p orbital, you're making, and then over here you're breaking bonds to that carbon sort of at the same time. And we know that carbon only forms 4 bonds, but you have this thing where it's kind of like 5. But again, since that's the highest point, it has to be the most energy as the mechanism proceeds. Question? This thing?
No, under the curve.
P orbital?
Oh, yeah.
So again, to highlight the inversion that's happening, with those colors, blue, green, and yellow. In the transition state, those hydrogens, because the carbon's sp2, those 3 hydrogens are now all in the same plane. So probably the cheapest example of this is like if you have an umbrella and on a rainy day, the umbrella is like one way, right, protecting you. Then a gust of wind happens and the umbrella goes the other way. So instead of like repelling, it's now like collecting. But when it does that, it hits a point where the umbrella is completely flat, right? It happens quick, but that's the inversion. So we go up in energy, and then overall, so this is the delta G part. The products are lower in energy than what you started with. And so those use other terms rather than exothermic and endothermic. Because it's delta G, the word changes a little bit. And so going up in energy, or delta G greater than 0, is called endergonic. When it's less than 0, it's exergonic. And the primary difference is the other stuff that's included in that delta G equation. I would say I'm 99.9999% sure that the transition state is always going to be greater than 0. You always have to go uphill. But this, it's not always below where you started. It still could be up here, but it's not going to be as high as the transition state. So the Gibbs free energy is described by this equation. And so we've seen this already, right? That delta H, that deals with the bond making and breaking. The new things here are temperature and delta S, where S is entropy. And tell you this, I really don't understand enthalpy. It's probably a little bit more confusing concept to really put your hands on, like what it really means. The word that I think about is chaos or order. Is the reaction proceed? Is it generating more order or more chaos? And that's what is folded into that term. Experimentally, that's probably the hardest to measure as well. But for the most part, I think what dominates the overall numerical outcome is the delta H term. So just keep in mind, when you're dealing with this delta G, you use these words. The exothermic and endothermic, that's associated with the delta H. So here is that rate equation again. We're not going to do too much math in here. This is a pretty simple rate equation for the most part. They can get wildly complex pretty quick. And that makes keeping track of these units a nightmare. So for the most part, the mechanism will inform you on the rate, and then you can make assumptions based on what you see. So what is the take-home message for this slide? The rate of the SN2 is really classified by the nature of the electrophile. So say, for example, if we were using the bromide, so methyl bromide, primary would be ethyl bromide. Secondary would be 2-bromopropane. And then tertiary would be 2-bromo-2-methylpropane. So you can sort of make your life a little bit easier and say, okay, if it's tertiary, it's not going to react by SN2. So in terms of rate, if you had a couple different substrates in the flask, this is the rate in which they follow. Methyl would go first, then primary, and then secondary. So let me just finish up this slide in the last minute here to explain why that is. So remember that the nucleophile has to attack opposite of the leaving group. And what we're looking at here is if you put your eyeball like right here, and you are looking down the sigma bond between the carbon and the bromine, and you are looking right at that antibonding orbital, which is now shown here as the blue ball. The nature of those three things will affect how the nucleophile can attack that antibonding orbital. So as you start substituting from H to carbon, 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 the space-filling model shows you that, okay, there is I can see the antibonding orbital. But as I add more carbons, you can gradually see that in the tertiary one. Now it's just that little space there. That nucleophile can no longer get in there, so it's not reactive. So the benchmark is shown here. in terms of secondary being sort of your benchmark of 1, primary is faster, and methyl's the fastest. So we're a little bit out of time, but that's not to say that tertiary substrates will not react. They react by SN1. So there's the connection between those two mechanisms.